Hello, everyone. A very warm welcome to you all. Thank you for joining this second episode of Nasscom AI Pathshala. I am Aditya Yelluru, Program Manager at Nasscom AI and the lead for the AI Pathshala program. Co-hosting today's session with me is my colleague Amrita Tripathi, who heads our branding and communication.
Thank you, Aditya. A warm welcome to everybody today. Nasscom AI Pathshala is a transformative initiative designed to close the AI skill gaps by providing practical, industry-focused training in AI and GenAI. This program fosters innovation, bridges the gap between academia and industry, and inspires students to pursue research, driving growth and long-term impact in the AI space. Today's session dives into an exciting convergence of technology and real-world challenges with the title of the topic as Advanced Demand Forecasting Techniques in Retail, a fundamental pillar of modern retail analytics. Demand forecasting leverages historical data, market trends, and advanced modeling techniques to predict future customer demand. In retail, precise forecasting plays a vital role in optimizing inventory, refining pricing strategies, and streamlining supply chain operations. These are the key factors in staying competitive and meeting the customer expectations. In today's session, we will explore how AI and machine learning are revolutionizing demand forecasting. We'll examine key time series algorithms, including SariMax, which captures seasonal trends and external influences, and Profit, powerful tool developed by Facebook to handle complex seasonal patterns and trend shifts in retail data. Through live Python demonstrations, you will also gain hands-on experience in implementing these models, evaluating their performance, and applying them to the real-world retail scenarios. Whether you are new to the AI-driven analytics or looking to enhance your expertise, this session will provide you with the knowledge and practical skills to make informed data-driven decisions in the ever-evolving retail landscape. We are delighted to welcome Asha Venugopal and Jenny Setia to lead today's discussion. Over to you, Aditya, to introduce our esteemed speakers.
Thank you, Amrita. Here's a quick introduction of our speakers today. Asha Venugopal is a data and analytics senior manager at BCGX. With 10 years of experience in the analytics domain, Asha has delivered substantial impact through data-driven analytics in retail and IG. She specializes in predictive analytics and has extensively developed solutions in demand forecasting, pricing, promotion effectiveness, and process parameter optimization. Welcome, Asha. Jenny Setia is a data and analytics lead at BCG with 8+ years of experience in the analytics, expertise in predictive modeling, so specializing in solution design for integrated business planning, assortment planning, marketing mix modeling, customer segmentation, and process parameter optimization. Welcome, Jane.
Thank you, Tito.
Over to you, Asha, to take the session forward.
Definitely. I'll quickly share my screen. We'll start off the session with some background of, what is demand forecasting, what are various algorithms that we use there, and why is demand forecasting important. And then towards the later half of the session, Jenny will take us through real Python examples of how we could be executing each of these algorithms in order to forecast demand, specifically in the retail perspective. Again, looking forward to having an interactive session with all of you. In case you have questions, please do leave them in the Q&A box, and we'll be able to take the questions up towards the end of the session. So first, I think in this session, like I already mentioned, you will learn 3 key things. First, you'll get an understanding of time series forecasting, what it is and why it is so crucial for predicting demand. Second, we'll explore how demand forecasting supports core business objectives. And here we'll specifically talk about minimizing stockouts, reducing markdowns, and maximizing the overall profitability. And finally, you will see a hands-on demonstration of these forecasting techniques in Python, giving you practical skills to, implement and as well interpret the results. And by the end of it, I think you will not just know theory, but also how to put it into action to drive better decision making in your field of work. I think moving on, let's see exactly why demand forecasting is so critical in a real business world setting, right? So demand forecasting is essentially the process of estimating future demand for a product or service. Again, in industries where production or supply has a long lead time, like manufacturing or large-scale retail, being able to forecast accurately is vital for planning resources, managing inventory, and also meeting consumer demands. And specifically, if I speak about retail, demand forecasting becomes a key part of strategic planning because retailers have to navigate seasonal spikes, promotional events, and also evolving market trends. And by predicting demand more accurately, businesses can minimize costs related to, overstocking or stockouts and ensure that, they're aligning their operations with the actual market conditions. And I think while going through the practical Python notebook, we'll see more about, how do we account for these factors while forecasting demand. Now that we are aware of, why demand forecasting is required, why is it important specifically for the ever-growing retail landscape? If we were to deep dive or double click into the application specifically in retail or manufacturing context, first it aids inventory management, like I already spoke to you about, by ensuring that the stock levels are balanced, neither too high nor too low. Second, it supports planning and scheduling. I think with reliable forecast, businesses can better align production runs and workforce needs, right? And third, it also informs markdown strategies. Knowing when the demand is likely to dip will basically allow retailers to time discounts effectively and also minimize losses. And finally, the fourth pillar, it guides an effective pricing strategy, basically by projecting future demand and adjusting prices in advance to, optimize profit. Overall, all of these use cases help businesses operate more efficiently, reduce costs, as well as meet the consumer needs in time. Right. Now that we know the typical use cases that are solved using demand forecasting, what I will now talk about is a method, an analytical framework, which is basically a 4-step process. And here we will talk about it more in the retail context. So if we would, the first step is to identify the right data elements required to estimate demand. And typically, the retail data set has about 4 very important data elements, which is your point of sales data, which has, weekly or daily demand pattern, your product attributes, which will basically help inform the level at which you would want to forecast your demand, whether it's at a category level or a department level, for example. And then, of course, an equally important part of it is the inventory and out of stock information to have an idea or to have an estimate of, how fast is this specific product going to run out of stock. And of course, there are, to capture real market trends, we need to be aware of both micro and macroeconomic data, which will be a crucial input to all the demand forecasts. Once all of these data elements are collected and consolidated in a feature lake, the next step is the exploratory data analysis and feature engineering. I think the single most important step before we build any sort of modeling framework, right? Here, the key steps are to identify the right product granularity. Of course, you need to work against averaging out patterns versus minimizing noise. If we were to predict demand at the most granular level, like a product level or an SKU level, we might be introducing a lot of noise in the data, leading to inaccurate forecasts. Whereas if we were to forecast at a too high level, probably at a department or a portfolio level, we might be averaging out patterns and we might not be able to accurately estimate the demand. So it's very important for us to, strike the right balance. And then the second one is identifying what the desired forecast accuracy is, and typically the forecast frequency, right? Forecast frequency depends on the business planning process, depends on why demand forecasts and how they are used, right? So if the demand forecasts are used for the quarterly planning cycles, or for planning the seasonal inventory that needs to be stocked up, probably we might have to forecast a quarter in advance. Whereas if it is for the annual planning with respect to financial budgets, then probably we would need a more longer term forecast, which is a yearly level, right? And then the third key component of ED and feature engineering is to create certain derived variables, like, discount might be impacting demand, holidays could be impacting demand. So it's crucial to have these inputs as a part of the EDA phase. Once the features are ready, we have the data elements in place. The next step is the analytics framework in itself. Like any other ML model, it's very important for us to split the data into train and test timeframes. The train timeframe is used to learn patterns based on historical trends, and then we can test out how robust the model is on the test data frame. Right. And then there are very specific, accuracy calculations for time series prediction. We'll speak a little bit more about it in the subsequent slides. We call it in-sample and out-sample forecast validation, wherein we'll talk more about it. I think just talking on the slide wouldn't be as helpful. And then, of course, there are a couple of accuracy metrics that can be calculated to estimate how accurate our forecast is before we actually implement it in a real world scenario. And finally, once the forecasts are in place, it's equally important to create interactive dashboards which are almost real time, that can be used by the business stakeholders, which allows the business users to look at the entire time series trend, look at what the forecast is, how accurate the forecasts are, and also have like a future forecast compendium. Again, we'll double click on each of these elements today as we go through the session. The whole analytics framework that I just explained can be visualized using this block diagram. So what we see here in the first step is the data extraction and cleaning, where the features are created. Then it is split into two data sets, which is the test and the train. Again, the methodology for splitting it into test and train could be numerous. We could just have a very simple first 70% of the data as train and the next 30% as test, of course, once it's sorted on time. Or we could also do various cross-fold validations, wherein we can test how the model is performing across different time frames. Now, once the training data is chosen, it feeds as input to the ML algorithms. We'll double click on a couple of these in the session today. We can run each one of these algorithms, assess the accuracy, and depending on what the accuracy is, we select one final model. And after selecting the final model, we forecast future data using the model that has already been trained on the past historical data. Which will then be leveraged to then populate the forecast reports. Right? The typical technology stack that we have seen could be for data extraction and cleaning, could be Excel, could be SQL. Clearly depends on the maturity of the organization you're working with. And the machine learning in specific can be done both in R and Python. Python, we will be demonstrating how each of these algorithms work in Python today. And finally, the output of the Python can then be fed into any visualization tools such as Plotly or Tableau. I think now that we know at an overall level how the framework functions, it's important for us to know the broad categories of time series forecasting algorithms that exist. Again, there are four critical categories: the traditional statistics, the Bayesian models, the machine learning, as well as deep learning models. If we talk about traditional statistics, anything like Arimax, Holt Winters, theta, all of these come under traditional statistics. Again, there are various advantages and disadvantages of each of these methods, right? So if we talk about advantages, the traditional statistics is well understood and it is easily interpretable. It's white box and works very well for small data sets. And in terms of computational resources, it requires minimal computational resources. Again, based on my experience creating such solutions for various clients, traditional statistics itself bring in a step change in the way demand forecasts are right now created. The only disadvantage of traditional statistics is that, it cannot capture a lot of nonlinear patterns unless we have external variables to capture that pattern. And when it comes to missing data, it cannot handle it structurally, but we can, ensure that the missing data is treated for before using traditional statistics. Right. And in many industries, we might also face that, there is some prior knowledge which needs to be incorporated in the model very explicitly. So when it comes to incorporating prior expert knowledge into the forecasting, that's where Bayesian models come into picture. Apart from just providing the forecast, it will also provide an additional parameter which helps in estimating the uncertainty in the predictions. It will give us a better hold on, what the error ranges are. And when it comes to small data sets, again, it handles it well. And if there are informative priors, that's an added advantage in Bayesian models. Again, the disadvantages are pretty straightforward. It's pretty computationally expensive, especially when it comes to large data sets. And since the model also takes prior as an input, which is the past information or expert input, that is very subjective. So depending on who the expert is and what kind of prior information they are providing, the forecast might differ significantly, right? So that's a disadvantage. And it is difficult to scale to high dimensional problems. I think that's just one small con of Bayesian models. The next set of models that we have for this purpose is machine learning. Again, you would have heard a lot of these terms like gradient boosting, support vector machines, random forests, etc. All of these come under machine learning, and it very well captures nonlinear patterns in data, and many a times overperforms in comparison to traditional statistics. Again, this works very well with missing and noisy data because usually it's either bagging or boosting, and in either of these techniques, outliers or missing data is handled well. And of course, we can incorporate as many external features as possible in the machine learning techniques, because multicollinearity as a concept is handled well in this branch of algorithms. Of course, it requires large amounts of data for prediction. Again, it's slightly more black box in comparison to traditional statistics. And that's the only con of machine learning. And it requires a bit of, hyperparameter tuning, which might get a little tricky, especially if you want to do it at scale. Then the fourth branch is deep learning, wherein we have recurrent neural networks, LSTMs, etc. Right? So again, deep learning will provide an accuracy boost definitely, but and can handle long-term dependencies as well as short-term patterns well in the data. But it is computationally very, very expensive, and you need very rich data source in order to deploy a deep learning model. If the data set is limited, deep learning and traditional statistics and machine learning almost perform very similarly. And just keeping the computation part of it, for small data sets, of course, the first three branches are preferred. And if you have very rich data, very granular data, deep learning is something that we can deploy. Again, today we will be focusing and going deep into the first branch, which is traditional statistics, and we will probably touch a bit on how do we extend it to other models that we have on the page here. Now that we know at a broad level, what are different branches of models that we have at our disposal, I think in this slide, we'll specifically explore time series and its key components, which is your trend, seasonality, cycle, and irregular effects. And I'll try to illustrate each of these concepts with some real world examples from the retail industry. Right. So first, when we talk about time series is essentially a collection of data points recorded at regular intervals. Regular interval is the keyword here. And if you think of a store's daily sales or the weekly footfall in a shopping mall, all of these are like classic examples of time series in retail. And by analyzing these data points over time, we can spot patterns, forecast demand, and make informed decisions on inventory pricing and promotions. Right. The first component of a time series is basically trend. Trend captures the overall direction, which is either the growth or decline of data. Right. So, for instance, a retailer might see a steadily increasing monthly online sales over a course of a year. And this upward trajectory, suggests a positive trend. And why is this important? Because identifying trends help retailers anticipate future demand and plan resources. Right. And the next component of it is seasonality. Seasonality again refers to recurring patterns in the data. That happens at regular intervals. And if I have to take an example for retail, you might see a spike in sales every holiday season, like Diwali in India or Christmas in the West, right? So these are typical seasonal components of a time series. Another example is weekly seasonality that could occur in a retail setup, right? So if customers shop more on weekends, you'll notice a consistent demand peak on Saturdays and Sundays. I think we'll bring this to life in our live demonstration as well. The next part of it is cycle. Cycles are like seasonality, but they typically span, longer periods and often align with, broader economic or business cycles like recessions or booms, right? In retail, an example could be, multi-year economic expansion that boosts the consumer spending, leading to higher store revenues, then followed by a slowdown. This is typically captured in a cycle. Then irregular effects are, sudden and unexpected events. It could be a product recall, a natural disaster, or a supply chain disruption, right? That can't be explained by any of these components like trend, seasonality, or cyclicity. And if, for example, if severe weather forces store to close for several days, you will see a sharp and temporary drop in sales. And that's the irregular component of a time series. Now, again, understanding these elements, help retailers forecast more accurately, of course. And by knowing what portion of the sales growth is due to trend and what's driven by seasonal peaks and what's purely unexpected, businesses can make smarter decisions about inventory, staffing, and marketing. So if I were to just summarize this slide, time series basically gives a very powerful lens to view the past performance and anticipate future demand. And with this knowledge, a lot of optimization in terms of operations can be done to deliver a better consumer experience. That's just a quick overview of time series and its elements. Next, we'll delve deeper into specific forecasting models to see how these concepts can come to life in real retail world scenarios. Yeah. Again, we've covered the fundamental elements of time series such as trend, seasonality. Let's quickly shift our focus on how do we forecast them, right? On this slide, we'll explore 4 popular modeling approaches. The first one is moving average, exponential, smoothing, Max, and profit. Again, each method has its own strengths, data requirements, best use case scenarios. We'll try to break down each of them in the context of retail demand forecasting. So moving on to the first approach, the moving average. Moving average takes a series of data points and computes weighted average over number of consecutive observations, right? It helps smoothen out short-term fluctuations, and it typically highlights long-term trends. In retail, a simple moving average can be used to forecast demand for stable products, where sudden spikes are rare. For example, if you track weekly sales of a basic household item, a moving average can offer a quick and a reliable forecast. One limitation of this method is that it doesn't adapt quickly to major shifts, like a new product launch or a sudden promotional surge is something that moving average cannot take care of. Moving on to the second, that leads us to the second category of model, which is your exponential smoothing. So exponential smoothing is similar to moving average, but it places a lot of emphasis on the recent data points. Again, this makes it more responsive to sudden changes in the data. And retailers usually use this technique for products that have mild seasonality or gradual trends, as it can catch those patterns without overcomplicating the model a lot. And again, if I were to talk about a typical use case, it's basically production and inventory planning, where a store might actually notice an uptick in sales after running a promotional campaign and want to capture that trend in real time. Right? Moving on to the next one, which is Sarimax. Sarimax again stands for seasonal auto-regressive integrated moving average with some external variables or exogenous variables, as we call it. It's an extension of ARIMA that handles for seasonality and external factors. Again, it's a good choice when your data has repeating seasonal patterns, like I mentioned, like holiday sales, or when you want to incorporate outside influences, such as economic indicators or promo events. And again, putting in context of retail, right? So if a retailer runs a monthly discount campaign, or if local festivities significantly impact their sales, Remax can integrate these exogenous variables effectively into the forecasting process. Again, this typically requires a bit more data, more computational effort, but can offer better accuracy when the right factors are included. Moving on to a slightly more sophisticated algorithm, which is your Profit. As you might all know, Profit is again developed by Facebook, designed to manage complex seasonality, trend shifts, and holiday effects with very minimal manual tuning. And it's useful if your retail data exhibits multiple seasonal patterns like daily, weekly, yearly, and you can expect abrupt change in trends like sudden surge in online orders during a new marketing campaign, right? These are typical use case scenarios where Profit comes in handy. And moreover, it provides intuitive parameters, making it user-friendly for someone who is starting off new and might not have very extensive a time series background. Right. Now, I think this slide just captures at a very high level what each of these techniques are. We will take a closer look at one of the more advanced models, which is Sarimax. Sarimax is again built on top of ARIMA family, which is again used for capturing trend, seasonality, and external variables all in one framework. Right. If I were to just speak about ARIMA, it has three parts to it. The first one is AR, which is the auto-regressive part of it. It basically measures the influence of past values on the current value. So for example, today's sale might depend on yesterday's or last week's sale. So that's something that the auto-regressive component will take care of. I in ARIMA stands for integrated component, which basically involves differencing of data to make it stationary. Basically, it removes trend or seasonality so that the model can capture the underlying pattern more effectively. The MA component of it is moving average. It accounts for a bit of irregularities or noise between two consecutive time points by modeling the error term based on the past errors, right? Together, these components will help us capture growth or decline in trend and also short-term fluctuations in retail demand data. Now, extending to Sarima and Sarimax, Sarima in itself adds another parameter, to handle seasonal patterns like weekly or monthly sales spikes. And this is critical where holiday seasons or end of month paydays can significantly impact your demand. Surrey Max, when we talk about it, goes a step further by incorporating external factors. And these external factors are typically called as exogenous variables. And these could be anything like holiday flags, discount percentages, campaigns that are ongoing, etc. Right? So it's usually useful when you know that certain events directly influence sales. By integrating these factors, Surrey Max is a more holistic framework, which usually provides slightly better and more accurate forecasts in comparison to AIMA or SARIMA. And I think we look at how to implement SariMax as well today in a practical Python environment, ensuring that you can leverage whatever theory I've spoken about now into actually implementing it in real time. And just talking about this slide, I think it just captures everything. ARIMA, it accounts for trend, it accounts for rate of growth, rate of change of growth or decline in the data, accounts for noise between data points. SARIMA, it's ARIMA plus the seasonal component. SARIMAX is SARIMA plus the exogenous variables, right? Now that we've understood, these concepts, a very quick, primer to profit. Again, profit, like I told you, uses an additive regression model and it has 4 key parts. First, it detects and models the overall growth using piecewise linear or logistic curves. So if your sales trend changes at certain points, profit will be able to pick that up automatically. Second, it handles yearly seasonality through Fourier series, which basically captures pattern that repeat year over year, like your holiday surges. And third, it includes weekly seasonality using certain dummy variables, perfect for regular patterns such as weekend spikes. Right? Finally, you can specify important holidays or events, so the model can factor in these variables also during the forecast. Again, this combination makes profit very user friendly and it's very powerful for capturing complex trends and seasonality, specifically in the retail setup. Now that we've touched briefly on what these algorithms are, there are 3 typical validation methods that we use in a time series problem. Right? The first one is MAPE, which is your mean absolute percentage error of whatever we are trying to model for each product. Again, this is very easy to interpret. It's unit dependent because it's a percentage metric, right? So what we basically see is in percentage terms, what is the deviation of the predicted predicted units against the actual units, and it's averaged for each product and each year, right? That's your MAPE. Now, the disadvantage of MAPE is since it's an average metric, it's very, very prone to outliers in the data. And in order to account for these outliers and ensure that, the error is not basically skewed due to one extreme error for a given product, we use the volume weighted MAPE. Now, volume weighted MAPE is just going to weigh the error metric by either revenue of the product or volume of the product. Now, moving on to the third metric, which is right. Now, moving on to the fourth pillar that I just spoke about, which is the insights and reporting part of it. Here, I'll just talk about a few visualizations that is very critical whenever a time series model is built. Right. The first one is decomposing the time series into its various components, like I spoke about. So something, the visualization that you see at the bottom of this slide is something that we can strive to have for each product that we are forecasting for. So we can clearly see the trend, whether it's increasing, decreasing, we'll be able to identify the seasonal pattern in the data, and we'll also be able to identify what is the residual noise. And if there is a feature that can be included for accounting this residual noise, we can as well include that as an exogenous variable. The next part of it is basically the actual demand overlaid with the forecasted demand. Again, this is a very powerful visualization wherein we will be able to see whether the predicted demand is in line with what the actual demand is or whether it's different. And it's important to view these plots separately for train and test data. And the second plot here also looks at how the forecast looks. Right? Again, our aim is to have both the lines as close to each other as possible, which indicates that the forecast is robust and we are able to capture or predict the demand accurately. Then once we scale the model across multiple product categories, what could be an interesting plot to look at instead of just taking average across all products is to look at error bins, right? We can create a histogram of MAPE buckets. Basically, within 0 to 10% of MAPE, what proportion of products are being forecasted? And within 10 to 20% of MAPE, what proportion of products are being forecasted, so on and so forth. Again, our aim is to have almost all products forecasted within 30% or within 20%. Again, differs from use case to use case and how accurate should the forecast be from business case to business case. So this is again a very powerful visualization to look at instead of just looking at one aggregate metric across all categories. Right. Now that we have covered why demand forecasting is important, how do we forecast demand using these algorithms? And finally, how do we assess if the forecasts are accurate? What are the benefits of it, right? Again, this slide just highlights 4 major benefits that we have seen across use cases that, an effective demand forecasting can deliver. First one is, out of stock avoidance, right? It helps maintain customer satisfaction by ensuring that products are always available. Second is markdown avoidance, prevents unnecessary price reductions on overstocked items, thereby protecting profit margins, right? And third one is working capital cuts. They come from more accurate inventory planning. So so that, you're not tying up cash in surplus stock. Finally, operational benefits, I think like streamlined logistics and improved supplier relationships, can emerge only when inventory levels are matched with actual demand. So altogether, these factors demonstrate significant value at stake in getting forecasts right. So now that, all of you have gotten a primer of, how do we forecast demand, what factors need to be accounted for, and how do we evaluate the models, we'll switch to a practical implementation of whatever we have gone through in the slides today through a Python notebook. And probably I'll hand it over to you, Jenny, to take us through the remainder of the session.
I think like we've talked about the different use cases in retail and what are the different types of algorithm that we typically use when it comes to statistical modeling for time series. What I'll start off with is some of the data sets where we can just talk about, how does the data look like, and we'll use the similar data to do some of the machine learning model on top of it and see if at all we can, fit a good model here and get some forecast out of it. So what you see here is an example where what we have is for a product one, we have the monthly sales starting 2022 January. We have what were the total units sold for that particular product. So this is how the data looks like, where we have product category, which says which category it belongs to, what is the product inside that particular category, and for each of the months, what has been the total unit which got sold in a particular store, you can assume. And if I just give you an example of, let's say, a category is nothing but, let's say, if I'm talking about apparel. So apparel becomes a category. Inside apparel categories, there can be multiple different, products which can come. So this particular data set which you're just seeing is just says that there are, for example, there's category 1 where you have product 1 and there can be multiple different products inside that particular category. Similarly, you can have, category 2, which can be, let's say, accessories, which can also have certain number of products available. So this is just a basic data set for you to understand how a time series might look like, or what kind of problems can be solved using time series there. So here you will see this particular data set to be used in the Python notebook as well, but just wanted to make you aware about how this particular data set look like. So typically the problems which comes in hand is, let's say I have the historic data or the historic unit which has been sold for that particular product, and the ask is, let's say if I have data till if I'm sitting in, let's say, February of 2023, and I want to predict that what will be my sales for the coming 3 months or a quarter, what will be the value here, so that my stores are better prepared, I have enough quantity available to cater to the demands of the customers. So these are some of the demand forecasting problems that we can typically see for any of the retailers, where they do want to make sure that they have the upcoming demand which is available for a few of the months, so that they can stock up their stores accordingly. So whenever we get a data set, there are some of the analysis that we do, or we look into the data to understand what are the different things which the data is telling us, right? So now let's say I just imagine that the problem statement is, let's say we have to forecast for the next 3 months as to what will be the units which will be sold. And what we typically look into is what are the total number of months which are available. So if you see here, for me to start running a machine learning model, I have close to 38 data points which is available. And you must have seen in the slide which Asha was sharing, typically it requires more than 2 years of data for us to understand how has the sales grown year over year, and if at all there are seasonality in the data, is there a year-on-year growth which is associated for that particular product. So we have 38 data points here for this particular data set. Before you start modeling any of the data set which comes to you, there are certain questions that you should be aware, which I think Asha touched a little in the beginning, where what we essentially first question that we typically ask is, what is the time granularity of the data? Is it monthly level, is it weekly level, or is it an yearly level? So or it can be as small as daily level data or hourly level data, and things like stock market might have like every second you can have some data or the other available. So these are some of the typical questions we have when it comes to the time series. I'm not sure if you'll be able to, maybe answer it in the chat. But let's say if I'm talking about this particular data set, if you have to guess what's the, time granularity of this particular data set, what do you think is the time granularity here? I think most of them are answering the right one, that it's at a monthly level. So what you see here is actually the end of month. So typically what they do is they record whenever, let's say if I'm talking about a store, they record for until the end of that particular month, what has been the unit sold. So for January of 2020, because there were 31 days, so this was the entire month units which was sold for that particular product one. So that's right. The data is at monthly level, right? One of the other questions that we typically see is, before we do any of the forecasting, is understanding what's the primary key, or we call it what's the level of data, meaning if I have to start predicting, at what level should I predict? So is it category level, or is it product level, or something else? So what do you think can be a good primary key to this particular data set that you see? That if I just identify the primary key, it's at that level that the data is at. So if you have to identify the primary key using this particular data set, what do you think is the primary key here? So the primary key is probably the product across the month, and the level at which we will probably forecast is month level. Is at product cross month level, because that's the granularity at which we have the data. So in case we want to, let's say, so typically what happens is, let's say we might want to also get at a category level what's the sales at that particular category. So once we know that we have forecasted for all the products inside that category, we can, do a simple sum up at a category level to get the enhancements there. So it depends upon the use case. For example, in our use case, we want to forecast. So if you see the problem statement that we have in hand is forecast for the next 3 months for product one. So we'll be forecasting for product one and at a monthly granularity, that for the next 3 months, what will be the forecast there. So one of the other questions that we ask is, how many years of data do we have data available? So before we start running any of the algorithms, do we even have enough data available? So if I have to talk about product number one, how many years do you see the data is available for?
I think one of the participants have mentioned 38 months.
That's the total months that is available. And when we look into years, so there are total of 3 complete years which is available, which is 2020, 2021, and 2023. So I see a lot of 3 years there. So that's right. We have 3 years of data available, which, ticks off the sanity checks of, do we even have enough data to start running a machine learning model? And typically, like I said, we look out for, do we have like more than 2 years of data to start understanding the seasonality of sorts. So we have 3 years of data, so we can definitely run a machine learning algorithm there. Right. So is it possible to run ARIMA or SARIMA or all the different types of algorithms that Asha talked about? Yes, because we do have 2 or more years of data available. On the other hand, if you see there is another product, let's say product 2, it has very limited, data points available. And unfortunately, we will not be able to directly use a machine learning model to start forecasting, because a total of 5 data points is too less for us to start running a machine learning model. That's why maybe for product 2, we might not be able to run the machine learning forecast. Here, simple things like maybe just taking the average of last 3 months, or taking the average, we can just come up with a potential value that on an average, you might be able to sell these many units. So it's not as good as a machine learning model, but maybe a fair estimation of as to how much should I at least keep into my inventory to make sure that things are working fine and I'm not getting into the situation of, getting into the situation of overstocking or understocking there. So for product 1, it is possible to run the machine learning model, but for product 2, it might not be possible to run the machine learning model.
And there is no set rule saying that, you need 5,000 data points, just answering to a question on chat. For any time series model, it is a must to have at least 2 years of data, because you will want to capture seasonality. The number of data points will differ largely based on what you're trying to predict is stable or whether it's volatile, right? So if the product is, probably in the mature stage and it has a stable trend, then probably 2 years worth of data at a weekly granularity could suffice. But if a product is very volatile, has just launched, or is undergoing, is towards the peak phase wherein it's a seasonal products, and there's a lot of volatility and variability, then you will require more number of data points in order to capture the trends better. So there is no direct answer of what the number of data points should be, but it largely depends on whether it's a stable trend or a volatile trend, and definitely 2 years is a minimum requirement.
Yep. Thanks, Asha. Moving on to the next question. So let's say if I have to run a machine learning model on it, what will be the dependent variable which I will probably put into my model to understand the trend here? So what column or which column will be the dependent variable if I have to start forecasting? So just a little bit of context about what I mean by dependent variable. So when I say dependent variable, it typically means what is it which I want to predict. So for in this use case, we want to predict the unit which will be selling for the next few months. So the dependent variable for which I'll be training my model will be the unit sold. So that is what we essentially call that as dependent variable. And whatever goes inside the model are called, either we call it exogenous variables, or which is nothing but, let's say, if I give trends to it, if I give holidays, if I give promotions, these are all the independent variables which will help us predict the dependent variable, or which will help us predict how many units will you be able to forecast for the month. So I do see someone, like a lot of you might have responded that maybe month is the dependent variable. That's not the dependent variable. The dependent variable is maybe units. Month could be like one of the independent variables which we give to understand that, let's say, if some of the specific months have higher sales as compared to the others, that can just help the model understand that, because let's say during holiday period people buy a lot of those units. That's why this can just help us explain. So month can be qualified as an independent variable, whereas unit is the dependent variable for which we will be running the machine learning models. So here, what we typically, for example, I told that we will be forecasting for the next 3 months. So the forecast period, which I say here, is 3. So typically, whenever you want to forecast, you should know that, okay, this is the period till when you want to forecast. So right now in our use case, we want to forecast for the next 3 months. So the number of forecast period becomes 3. One of the important things that you'll see in the Python implementation as well is, many a times what we do is, if the forecast period is not very huge, we typically consider the size of the test. Before that, let me just explain what is train and test. So whenever we run a machine learning model, we typically divide them into, we take our entire data set and we divide it into 2 parts. One is the training part of it, meaning we will show this to the machine learning model and tell them that, okay, now this is the training data set. You get trained using this, identify the different trends, identifying the seasonality, and identify, which all variables are leading to higher sales or lower sales. So this is the training part of the machine learning model. The remaining part is the test part, where what we do is we essentially don't show this to the machine learning model, and we run the machine learning model only on the train, and then forecast or predict it for the test period, and try to see that, is my model able to generalize it better? Like whatever it learned during the training time, it's basically a test for the model, that are you able to still predict even if you have not seen this particular data set. So that's what we typically do. We divide it into train and test, show it the entire training data set, and for the test period, we just keep it hidden. We will have those values available with us, but we will keep the actual value hidden from the model. And once the model gives us the prediction for those 3 months, we will then compare that, is it very similar to the actual value that we actually see in the data set, or it's not very well. There are areas where your model might perform very good when it comes to the training data set, but it is not able to generalize, or is very overfitted. That's the word that we use, that if the model is performing very well during test, but during train, but it is not able to perform as better in the testing data set, we typically say that it's an overfitted model and might not be the best model to start forecasting. So what we typically do is, in order to identify the train and the test window, we first look into for how many months do we want to forecast. So let's say here we want to forecast for 3 months. Typically, whenever we want to do a short-term forecast and we don't have to have a lot of long-term forecast available, we prefer to keep the test period similar to as our forecast period. So for example, if you want to forecast for 3 months, the test period that is advisable, of course, it's not necessary that you always take that, but it's advisable that we can keep the similar test period so that we say that, okay, we have tested it on a 3 months of unseen data, and then we are forecasting. So we can assume that whatever error which will be there in the test period can be similar to what could happen to the forecast period as well. So if I have to just split up the data set, the last 3 data points will essentially be my test data point, which we will not be showing. You'll see in the later implementation in the Python that we will not be showing this data set to the to all of the models. We will just get it trained on these and then try to see that how is it able to predict for the test. So the thumb of rule is that whenever you the deviation between the train and the test should not be high. So if you're getting a weighted MAPE of let's say 10% for train, the test should be, let's say, in and around you can say 8% to maybe 12%. It should not be very high for any of the machine learning model. So that's what we typically do. You'll see in the Python code coming up that we have done something very similar and trying to see if our model is able to generalize by keeping these hidden. So we can take 80-20, but one of the things to remember when it comes to time series is we can't really, so whenever we take 80-20 in traditional machine learning, what happens is it randomly selects 80% of the data, meaning it can select few months like this, and then randomly picks, for example, this is our training data set, and let's say we have these data points selected as testing data set. When it comes to time series, we can't really break a time series and consider this as test. It has to be like the last few 20% can be the test, and the remaining is the training data set. So it has to be a continuous series, and test should always be like kind of the last or the tailed portion of the time series that we have. So 80-20 could be applied, but the 20% should always be the last weeks or last months or whatever granularity of time period you have. It can be that, but not that you can break a time series off there. So that's one of the major differences between a traditional regression where 80-20 can work if you just take random samples, but here random is not an option because we don't want to break up a time series. Moving on, once we understood and we are comfortable with the data that we have, the other thing that we typically do is just to visualize that if we just visualize, so it's exactly the same data set. And if I want to just visually see what is happening to the growth, are we growing or are we not growing? Are there any specific months where we see peaks happening? What's the state of the business? Basically, something which can just help us understand, can be understood by using a trend chart like this. And you'll see, just by looking at the graph, you will be able to see a lot of things happening in this particular time series. So I think I can just probably ask, let's say if it's about growth, what do you think? Is it increasing year on year or is it decreasing? You can probably use the Q&A, section to answer. Like, is it a decreasing trend or is it an increasing trend? We do see that it's slight increasing. So the way to look at is let's say if I just fit in a linear line, it will be something like this, where it will just say that, okay, there has been an increasing trend from where we started, like 2020, and now we are in 2023. We will be like, there is an increasing trend. Is there any specific month which stands out across the year where we do see that some of the sales or the sale really peaks up during that particular month? So we do see that majorly during the time of December. If you see, we do see the sales are pretty high. So you can consider this, maybe this is one of the US retailers where you see a lot of sales happening during year end because of the Christmas, Thanksgiving, and all of those, which gets ultimately accounted in the month of December. So few things why visually just looking at it and getting up, understanding the data is important is a lot of your independent variables can actually be driven just by looking at it. So we know that we might want to add a December flag because we do see a peak happening there. So the model should be able to understand either by seasonality that year on year it is an increasing trend, plus during the month of December there is a spike which will happen because usually people buy this particular product a lot during the time of Christmas or end of December. So these are some of the characteristics that we typically look into before we move on to any of the machine learning model, just to, at a high level, understand what exactly is the state of the business, how is it performing, and are there any, prominent features which can just be added to the machine learning model just by looking into the trends that we have. Yeah. Apart from that, I think Asha has talked about, some of the accuracy matrix that we have, but I'll just maybe touch base a little on this because we'll be using, these two metric, mean absolute percentage error and weighted mean absolute percentage error during the Python code. So just for you to understand that, let's say we run a machine learning algorithm and we get these prediction, that these are the prediction for my train period, and we have the prediction for the test period as well. So let's say this is my test, the last 3 data points, and the remaining is my training data set. What we typically do is, in order to see how good is our model performing, we try to calculate the mean absolute percentage error and weighted mean absolute percentage error. The way to do it is, I know these are my actual values, and let's say I run a machine learning model, and this is what it predicted basis whatever it has learned from the dependent variable. What we typically do is we calculate the error, which is nothing but actual minus predicted. How many units are you off? So for example, in the first use case, the actual sales was 29 units, but the model predicted that it's 500 units. So you were 471 of the actual value, right? That's what we do for all the months. So that's the error that essentially is there month over month. Then what we calculate is the absolute, or you just calculate the percentage, which is nothing but your actual minus predicted divided by the actual value. So what percentage? So if I just talk about the, maybe the second example, so what you're essentially doing is your prediction is 64% less than the actual value. So the actual value was somewhere about 661 units, but you predicted it to be 239 units. So the error percentage that is somewhere about 64% of the error is there in this particular month. Then what we typically do is we just take an absolute just to get an overall average, and not so if you just don't take average and take a mean, it might get the positive and negative might cancel out each other. So typically, just to get on an average what's the error, we take an absolute, which is nothing but if at all it has a negative value, we just make it positive to understand that on an average what's the error there. So this is the absolute error. And when we talk about weighted or MAPE, it is nothing but it's the average of the absolute percentage error. So we just simply take the average and say that this particular, if this is the prediction, the overall MAPE of the time series is 84%. And typically the way to look at is, accuracy is nothing but 1. So these are the error percentage. So it's not a good model. Like your error percentage is 84%. Which essentially means your accuracy is somewhere about 16%. So it's not a very good model. So that's the MAPE value that we have. Typically what happens is we most of the times consider weighted MAPE because what happens that maybe the MAPE is getting biased towards a specific data point. For example, if you see the first data point, it is actually very off. And if you see it's somewhere about 1600% error, you see that the units sold for that particular week was very less. So what we do in weighted MAPE is we just take or weight by the actual sales. So this is nothing but the absolute error multiply by the total units that was actually sold. So we are just weighing in that if at all very less units were sold in that particular month, it might be the case that it's not very important. It's not a very important month for the business, and we might want to focus on the months which are really very important. So here we just give a weightage to all. Right now I've just given the weightage criteria as units. Many a time we give revenue weighted. So if we have the revenue associated, it might happen that we might want to just consider some of the high revenue contributors. So we consider weighted MAPE, where we just weighted by the units sold and just multiply it by the weight that we want. And the way we calculate weighted MAPE is we just take the sum of this divided by the sum of this, which is nothing but a weighted average basis the units sold for that particular month. So these are the two accuracy, matrix that we will be talking a lot about it. There are a lot of other, accuracy matrix, like it could be R square, it can be, the mean square root error. A lot of those are available. So it totally depends from use case to the use case. Which one do you use? Typically, we look at weighted MAPE to, understand how well is a model performing. So you'll see that once we start running the different algorithms, we will compare them basis their weighted MAPE or the MAPE as well of how well it is performing for the test. With that, with this entire context of once we receive the time series, we look into what is the granularity, what's the primary key, do we have enough data to predict? Then we look into, once we start visualizing it, are there any specific trends or themes which are coming out of it, which could actually be used as, independent variable to the machine learning model? And then finally, once we have the prediction, can we come up with some of the good accuracy metric to compare between different algorithms and try to see which algorithms is the best for our use case? Moving on, I'll just probably just quickly share my notebook as well. Let me know if my notebook is visible. Yep. Can you guys see my screen?
Yes.
Perfect. So this is, so we've just created a notebook which will give you a brief idea of when you get a data set, and you know that you might have like a suite of algorithms that you might want to run and try to see that which algorithm is actually performing the best. There are few things that you really do before even start jumping into the algorithms. Apart from what you just saw in Excel, there are some of the time series checks that you apply, or time series things that you look into once you start doing it. So like just few of the introduction to the notebook. So the notebook could be like, it is applicable, it's made in a way that it's very easy for you to understand. So even if you're a beginner, you will be able to understand what is happening in the code. Of course, a little bit of idea about Python and statistic is important, but it's not that it's very difficult to implement. It's something which is just being done on the normal laptops, and would really require a GPU or something for that. And if any one of you who is just interested, or it's kind of a refresher for anyone who would have used it some time back but want to just refresh as to what are the different techniques which are available, those can be benefited using this particular notebook. And in case you want to compare different time series technique as to which perform best versus the other, this can be a good starting point. And typically what happens is, it's not that one algorithm is the best. It totally depends from your use case to the other use case as to if it fits to your use case. It might happen the simple model might work. And if it doesn't fit, it might happen that the most complex model might not work, and you might get the result using just some of the simple algorithms. So it totally depends upon use case to use case. So you have to try out different algorithms and try to see that which accuracy metric has, which algorithm gives us the best accuracy metric, and we go ahead using that particular algorithm there. So some of the things that you'll learn is, it'll be simple introduction, which just Asha took as to how does a time series looks like. And then, some of the concepts that you'll see in this particular notebook is what is stationarity, and there are different algorithms which is entailed under the ARIMA family, and we do have a touch base on the profit algorithm as well, to just give you an idea as to how and different algorithms which belongs to ARIMA, and how does profit work if we want to use a time series using the profit algorithm. So what exactly is time series? What we do is, most commonly, time series is nothing but, like you just saw, it's equally spaced. If something is changing over time, that's essentially the definition of time series. So what we look into is, if whenever we get a time series, it has to be ordered chronologically. It should not be the case that it's not sorted by date. You should first sort it by date, and it should be chronological order, like you would have seen in the Excel which I was presenting, that it was in the order starting 2020 till 2023 in the decreasing order of the month. So we had it in the chronological order. So whenever you give it to an algorithm as well, either you have to convert it into a time, a Python date time format, so that Python can understand that, okay, this is a date format, and it will automatically be able to understand or sort it by date to better suit some of the algorithms. Apart from that, so time series can be broadly divided into two parts. It can be univariate time series, where essentially we just take the maybe the previous lag terms or the averages, just the time series itself, without even using any of the external variables or any independent variables. So it can be univariate, or it can be multivariate. When I say multivariate, meaning we also look into adding external features like holidays, promotions, or any of the special events which might happen for specific products. So we add those, and those are called multivariate, where it is also dependent on some of the other external variables. So I think Asha's already touched base on the different use cases and importance of why time series is important, specifically with respect to the retail scenarios. I think Asha talked about the demand forecasting. How is it important? And it's very important for you to at least get a gauge of what will be the demand for the upcoming months, so that you can stock up your inventory, and also ensuring that it is. So, for example, if it's a perishable product, you might not want to do a overstocking, because ultimately you know that particular product has a shelf life, and if it expires within the time period which has been mentioned over the packages, if it's an edible product, or if any specific product which has a perishable shelf life might get expired, so it's better to not overstock anything. So inventory rebalancing is one of the major use cases which a lot of retail folks work on, to make sure that they're not overstocking or understocking their things. Ultimately, there are things like, if you want to predict what will be the footfall for my particular store, that's also one of the use cases which can help. For example, if I'm a store manager, I want to probably have enough people to cater to my customers. If I have a decent idea about how many people will be visiting the store, and translate it into, if let's say if there are 1,000 customers who will be coming, I should have at least 10 customer support people who could cater to those. So in those type of use cases, identifying what will be the footfall, making sure that customer has good experience when they come into a store. It can be, apart from the customer customer support group, we can also have like, how many billing counters should you have. So if you know that there are a lot of customers coming maybe during weekends, you know that you need to have a lot of staff at your the billing counters, or the number of billing counters active should be very high in order to cater to the footfall, so that it has a good and seamless customer satisfaction. Otherwise, it might happen that if they have a bad experience, they might not even come or turn up into the store. So those kind of use cases are typically very important for you to have a good customer satisfaction there. Apart from that, there are areas where if we have enough data available, personalized promotions could be one of those other things, where we try to understand that what kind of promotions are working well, and if we tweak a little with the promotion, does that inherently increase the basket size of the customers who are coming into the stores. So there are like plenty of different use cases which can actually help us In retail, when it comes to time series, it's just totally depends upon which time, which particular problem is pertaining to your, if you're a business person, which particular problem do you want to solve first, and if you're someone who is working with any of the retail clients, what kind of problems will add if value to their existing analytics bandwidth. So I think these are some of the retail use cases which you can think of. Of course, it's not exhaustive. There are a lot which can still be added to this particular suite. So very simply, if I just have to explain the few components of time series, is we have the trend, we have short-term momentums, which is nothing but some of the seasonality or the cyclicity part of it. So when it comes to short-term, we have seasonality, but when we have, like, let's say, years and years of data, and we could actually identify what's the pattern which is going on, it's essentially cyclicity. Usually we have seasonality. Cyclicity is something which probably, if let's say you're identifying, or you're probably saying power supply or things like that, where you know that you will have a lot of data points available, cyclicity might play a lot of role there. But typical scenarios where we have 3-4 years of data available, seasonality might be more prominent as compared to cyclicity. And then we have the irregularities there. So if I just have to simply take an example, let's say if this is my time series, what we say is this is my trend, meaning I know that it's an increasing trend. And from a seasonality standpoint, it's kind of a sinusoidal curve. So if you just maybe marry both of them together, you will get something like this. But of course, there will be some of the things which will be unexplained, and you might not be able to replicate this entire series. That could be explained by some of the errors which are there. Many a times these errors are repeated errors, which using the machine learning algorithms, we try to come up with a decent function of that error and try to add to the to the curve which we get using this. So it's essentially trend plus the seasonality plus the error term, which ultimately help us get as close as to the actual value here. So that's with respect to just a time series. Now, like Asha was mentioning, that we have a lot of algorithms which can help you, solve a specific type of, forecasting problem. It can be smoothing based, where you consider, things like whole winters or exponential smoothing or simple smoothing or moving averages. So these are like smoothing based techniques, where that this is how your trend or your demand looks like. Can you come up with a function or a curve which can best explain it? So that's simple smoothing based techniques. Apart from that, things which we'll be deep diving a lot will be with respect to ARIMA. So in ARIMA, we have a lot of different kinds of models which falls into this particular umbrella, where we have AR, MA, ARMA, ARIMA, SARIMA, ARIMAX, and SARIMAX, with its special, like you from one algorithm to the other algorithm, when you move, you'll see that there is some new parameters which is introduced, which will be able to capture one or the other components of a time series to make it better. It might be the case that maybe Sarima is performing the best for you. We're not saying that one algorithm is better than the other. It totally depends upon your use case. Maybe what Arimax can do, it might be the case that you don't have enough seasonality, and Arima is the right model for you, but it totally depends once you run it and you see the accuracy of how well is your train and test performing. That could be a good indicator of which is the right model that you can choose. And then we do have other models like VAR models, or the unobserved component models, or the random walks. There is a fourth suite which says like the machine learning algorithms, which are like not directly made for time series, but we can customize it. For example, it can be XGBoost, Light GBM, and everything can also be used as a time series model, but they have to be fed into those specific features. So we can make it work like a time series, but we have to, explicitly give it some of the trend variables, some of the seasonality variables for it to start learning there. So majorly we'll talk about, the ARIMA-based techniques, as well as touch base a little on the profit algorithm, because that's many a times outperform a lot of different, traditional models there, because of the inherent property of capturing some of the external noises and outliers and missing values. So we'll touch base a little bit on profit as well. Moving on, like I explained, there are multiple different, accuracy matrix that we have. It can be R-square, it can be mean absolute error, mean square error, or RMSE. This particular notebook will typically talk about MAPE, mean absolute error, and the weighted mean absolute percentage error, which we just discussed in the in the Excel. Moving on, we've just defined some of the helper functions, which will just help us get the values out. So this is just nothing but the whatever I explained in the Excel. It's just the Python implementation where we just want to get the mean absolute percentage error. You'll see in the notebook further, I'll be calling these functions to get the MAPE and the weighted MAPE for each of the algorithms that we'll be running. So typically, whenever we start with Python coding, we have some of the custom functions which we can write so that we don't, so that the code looks a little cleaner. And apart from that, there are plenty of different libraries which are pre-built for time series, which we can directly leverage without having us code a lot of complex algorithms there. So this particular section, we're just importing some of the relevant libraries, because we are dealing with the ARIMA family. This is probably the most important line, where you'll see in the code below that this entire function Sarimax can actually help us implement AR, MA, ARIMA, everything, basis the different parameters that we can set. So it's just the importing of some of the libraries which can help us, better either understand the different time series or to run different types of algorithms there. So you see, I have imported profit as well, which you'll be seeing that we'll be implementing in the end. Similarly, if you want to import any of those external, so there are pre-built libraries for getting the R-square, mean absolute error, and so on and so forth, which can be imported and can be used for evaluating different metrics. So moving on to the first data set that we have. So you can consider that I have, let's say, there is a retailer, maybe it's a very famous retailer, which has his first store, which was available in 1949. And we have the footfall as to what was the footfall starting that particular year. So we have the data at the year-month level, and we have the footfall. The footfall right now, you can assume that these are the total number of people who entered the store during that particular time. What we typically do is, let's say if we have imported the data and we just have like what has been the footfall over the years, we can do some simple things as to like simply describe, which essentially mean is it will just give us the distribution of how the data looks like. So if you just see here, it just essentially gives you what's the median or what's the mean footfall, meaning what's the average footfall that has happened over the last few years. What's the 25th percentile, what's the 50th percentile of the median that we have, and what's the maximum number of people that has ever visited your store. And if you see that we have data from 1949 till 1960. So this is just an example that we have taken, like not related, may not be very much applicable in reality, but just to show you how this particular data set looks like. We just have month, year, which is the date column that we have, and this is the dependent variable which we might want to use if we want to forecast the future footfall. So what we typically do, like I mentioned earlier, is whenever we import a data set, by default, Python will not be able to understand that which is the date column, and you would want to explicitly convert that particular column into date time format, which Pandas library can just help us quickly do it. We have to just explain that in what format. So right now the format, if you see, is an year month format. That's why we've just mentioned that it's in a year month format for Python to understand that, okay, this is the format in which it needs to understand year. And if you see, once we've converted into the year month, it understand that it's a date time format, like you can see here. We've just converted into index for simplicity purposes. And we'll just see that, okay, these are the different dates which are which are available with us, which can be used as the part of year month column. Typically what we do is, for the sake of simplicity, we've just kept it that there's no outlier or there is no null value in this data set. But in real life scenarios, you might face issues like there are a lot of null values in your existing training data set. And there are algorithms, specifically, let's say ARIMA models, they don't really work if at all you have missing values. So you can impute the values. It can be simple imputation, like imputing it with averages, or imputing it with, let's say, one specific month is not there, we can probably replace it with by previous year similar month, what has been the ratio, or moving average of the last completed 3 months, what was the average, and then we just impute it. So like rule of thumb is, whenever we have the data set, we have to see if at all there are null values. If at all there are null values, we need to do imputation to make sure that we have a decent time series to give it to the machine learning model. Apart from that, there might be areas which could be outliers. For example, in the Excel which I was showing, the first row, on an average, I think all the sales value were above 200 or 300. Only the first row had 29 units. It seems that the data has some issue that could be a potential outlier. So might not be a real number, because it's way off. It might happen that maybe it is just capturing the last week of that particular month. So all of those things needs to be taken care of. So whatever you can do to make sure that you remove some of the outliers, you impute the missing value. That's typically the starting point, that you have good data points available, or the time series should be decent for the machine learning to learn. So better the time series is, better will the model be able to understand the actual trends and not get really distorted by some of the outliers we have. Things like ARIMA, they do get impacted by the outliers that we have, but Profit has inherent property of identifying outliers, so it will be able to take care of it. It's very versatile that way, is Profit, but there are a lot of parameters that we can tune to get or fit to that our use case, so that Profit can perform well there. But it requires a lot of fine tuning for us to start using Profit there. So with that said, once we know that there is no null value and the data seems good, we can move on to visualizing the data, or just start off with some of those important things. Other topic which just wanted to give a brief about it, because we will be using this particular term very frequently when it comes to time series, is stationarity. So whenever we want to use any of the models inside the ARIMA family, one of the important criteria is it has to be stationary. The time series needs to be stationary. What I mean by stationary is that it's the mean of the time series and the variance should be constant over time. So as the time passes on, it should not be that the mean is deviating a lot, or the variance, which is nothing but how distributed your data is across the mean value. It should be constant over time, and it should not be changing. That's one of the criterias of of using the ARIMA or SARIMAX model. Many a times, or most of the times in real life, you will not get a stationary time series, and you have to do some of the transformations to make it stationary. We'll talk about what kind of transformations will be required in order to make a time series stationary, but this is one of the critical assumptions that ARIMA or SARIMAX model takes into account, that whatever trend or time series that you input, it has to be stationary. In order to just look into is your time series stationary or not, there are multiple ways of doing it. You can visualize it, and just by looking into it, you can see that, okay, if at all there are, you will definitely see that the mean is not constant, or there is a huge variation. There are plots like ACF plots and PACF plots, which can help you identify, what could be the, is there a differencing which is required or not. And one of the things which we'll be deep diving is Dickey-Fuller test, which essentially tells it's just a statistical test which takes into account, or which takes your time series as an input and ultimately gives you a significant score. And if that score is less than 0.05, it means it's stationary. If it is not, then you have to do some transformation on top of your time series to make it stationary. So right now it's the same footfall example, which we've just visualized using the plot function in Python. And what you see here is from year over year or month year level, how is your footfall increasing? It might be the case that the retailer might be opening more stores, or more people are getting familiarized that there's a store opening, kind of a thing. So we do see that there's an increasing trend, and there's a seasonality as well. So let's say if this is the time series that you input, and we want to identify if it is stationary or not. One of the ways is just simply plotting it. So what I've done is, across the years, I have just taken the box plot, which essentially talks about, if you see this particular, the middle line is nothing but what's the average value, and here it's nothing but what's the distribution. So what's the the minimum IQR and the maximum IQR. So for each of the year, we do have 12 months available. So for all of those months in 1949, how does the the distribution looks like of the footfall? Similarly, across the year, if we plot, the idea is to first check. So the two criteria is, one is it should have constant mean. So if I just look into mean, if you see that the mean here is this, for this, the mean is somewhere about 150. And similarly, as in from year over year, the mean is changing. So the first criteria, that it should have constant mean, it's not fulfilled. So definitely it's not a stationary time series. Similarly, if you see variance, the variance is also not something which is constant. We see that there are different variants. Here it might be a little closer to the mean as compared to the like here, where it is very far off from the mean. So both the criterias, that the mean should be constant or the variance should be constant, is not met by this particular time series. Just visualizing your time series data. Another thing which I was talking about was the Dickey-Fuller test, which is a statistical test which we do to identify if a particular time series is stationary or not. Here, what we've done is, if we just apply this particular, so this is the Python code where we are just importing the Dickey-Fuller test here, and trying to see what's the and split out some of the values, like what's the p-value, what's the test statistics, and everything. So we will use, in case you just want to apply the Dickey-Fuller test, you will see that for this particular time series, it will definitely be greater than 0.05, meaning some transformation is required. And like I've been talking, that there are a lot of transformation that we apply. It totally depends from one use case to the other use case, which can fit into your use case. So typically, some other transformation that we apply is log transform, which is essentially nothing but taking your the dependent variable and just applying a log transformation on top of it, and then visualizing or using the Dickey-Fuller test to see that if it has now become significant or not. Other could be, and this is most of the time used in ARIMA, SARIMA, and SARIMAX, which is nothing but differentiation. So here what we essentially do is, let's say this is our time series, we can call it TS. and we will have it across different months. Let's say it's at monthly level. What we do is the time series of difference one is nothing but if you just differentiate. So if I have to get the value for this will be nothing but what is the value over here minus the previous value. So we will just have that is nothing but differentiation at one, like we just use the first one level of differentiation and differentiated by the prior values. Similarly, if you want to do the differentiation for 2, it means nothing but, let's say if it's the third term, we just subtracted by the first value. So there are so once we have the d is equal to 1, which is difference for one level, d is equal to 2 will be using this as the primary series. We again apply a differentiation of order 2 on top of d is equal to 1. And we do that till we get a stationary time series. So if I'll just take an example, if I use the same data set and just apply a log transformation, so this is how it looks like. It looks like the variance or the mean has stabilized a little, but let's apply the Dickey-Fuller test, which is the statistical test on the data, and try to see if it has become, if it has become stationary. So you see that the p-value is still 0.4, meaning it's not stationary yet. Other is differentiation, where let's say if we take first order differentiation, it has stabilized a little, but if you see the Dickey-Fuller test, it still says that the p-value is 0.05. It's close to 0.05, but not exactly 0.05. If we take like at the second order differentiation, does it now become stationary? It is comparatively better than what we've seen above. And if you just look into the p-value, it is less than 0.05, meaning this can be a good enough series for you to start putting it into your ARIMA models to start forecasting for the future period. One of the key things to note is that because we are doing any transformation on top of our actual variable, the dependent variable, ultimately what we'll be forecasting has to undergo a reverse transformation. So we can so this will ultimately give us many of the algorithms internally do it because they understand that we applied first order of differentiation or second order of differentiation, and will ultimately split out a value which will be non-differentiated value, meaning it's the actual value. But in case you're writing your custom algorithms, it is you have to definitely do a reverse transformation to get the actual value rather than using the using the outcome, because here you are playing around with the dependent variable itself. This will become the new dependent variable. You will add in all the different exogenous variables if at all you want to add, and once you get the output, that has to be re-engineered to get the final variable. So either you have to redifferentiate or do the exact opposite of what you did during differentiation to get the final forecast. Yep. Similarly, you can like if it's done here, we're good and we can just move on. But there are other things like you can take a log and then do a log differentiation to see if it's helping. It is still getting closer to 0.05, but not exactly closer. So maybe here, if you have to just make it stationary, order 2 differentiation can help you do that. There are 2 types of differentiation as well. Like either you the order 2 can also mean that you take the similar series and on top of it apply a differentiation, or you simply shift your time series by 2 unit and then do it. Typically what we do is we take this particular series and make another differentiation on top of it to get the second order differentiation when it comes to ARIMA or SARIMA there. So just for the illustration purposes as to if we have to make, how does the stationary time series looks like, we just subtract, taken the second order here. But typically it's applied on top of this particular time series. Moving on, I think Asha already touched based on ARIMA of what do we have. So there are 3 terms which are inside ARIMA. One is the AR term, which is autoregressive. I is nothing but the differentiation, which is what is the how many times do you need to difference, which is in order to make the time series stationary. And MA is nothing but how many error terms should you be taking into account to get your time series less prone to errors. So these are the three terms, and typically in while coding, what we look into is for AR, the term we use is what is the p value. So it is called by the we call it the parameter p, small p. I is nothing but D value, which is the differentiation. How many times do you want to differentiate your time series to get a stationary time series? And MA is indicated by the value Q, which essentially means is how many error terms do you want to add in order to capture the randomness that you have in your time series. Then what we have here, so these are the different ARIMA family. We might include exogenous. Exogenous is nothing but do you want to include independent variables additional apart from the time components? Those are the exogenous variables. So if we include it, it is indicated by the value X, which is nothing but exogenous. And if you don't want to include it and just want to make it a univariate time series, ARIMA and SARIMA are the things that we can use. Before the break, we'll just start off with given the similar time series data that we saw, which is the customer sales data for product number 1. We just created the similar data here, and we're trying to say that if at all, if we have any of the ARIMA models which can help us get a better forecast for this particular time series. So it is nothing but we just created this particular data set that you just saw in the Excel, which I was presenting previously. And we're just saying that the starting date is from January of 2020 till we need 38 months of data, which is exactly what you saw in the Excel as well. So we've just created a pandas data frame, which will have all of these things available for us to get started. So if I have to just show you how the data looks like in Python. So if I just look into the head of it, what you'll see is it's a series where we have the date column as the index of the series, and all the units as the values in this particular series. So what we are doing here is like I was explaining that let's say if I want to consider the 3 weeks as the forecasting weeks, we are essentially considering is the entire test data is nothing but the last 3 months actually as our test period, and the remaining is our train period. So we're just doing a train and test split basis that we're just considering the last 3 data points as your test and the remaining as your train. Once we have that, let's say if you want to fit a AR1 model, meaning autoregressive one. Autoregressive is nothing but it's the p value, which essentially means that if I have a time series, how many like let's say if at time is equal to t, it is dependent on t minus 1. So that's AR1. AR2 is essentially it is dependent on t minus 1, as well as it is also dependent on t minus 2. So it will have both the AR1 and AR2 incorporated. So that's what the AR model typically says. And like I was saying in the beginning, we can use the Sarimax model. We did have like ARIMA or normal AR models which were there. Nowadays, what we see is all of those have become quite deprecated because Sarimax as one entire function can help you implement all types of models. So if you just put 0 for, the way to read this is we have the Sarimax function, which is nothing but a library which is pre-coded, and we're just using that particular library which we just imported on top, giving it the training data set, meaning all the data points which is in the part of the training, and we're just mentioning what is the order. So the way to read order is the first term of order indicates the P, which is AR term. The second indicates the differentiation. How many times do you want to differentiate the time series in order to make it stationary? And the third term means the Q value or the MA value, meaning how many error terms do you want to, the prior error terms do you want to include in order to explain some of the error abnormalities that you might have in your data set. So if in case it's a AR1 model, we make the D and the Q term as 0 and make the P as 1, which essentially means it's an AR1 model. So if I just, read in the data and run the time series model here. So here what happens is whenever we want to fit a particular time series model, we just create an instance of the model and use the dot fit model, which essentially what it will do is it will understand the trends which are happening in the test in the trained data set and then try to come up with the forecast. If you notice, I have just given trained during the time of training. The model has not seen the test data frame or the test data points that we have. So right now, if you see here, if you want to predict, we can just use the test data to predict. So we have trained the model here. The model has gotten trained. And if you want to predict for some time interval, so for example, here we are predicting for the entire test period. Where this will do the prediction for the test period. And usually, like Asha was telling, that we do actual versus predicted trend chart. We create a chart like this, which helps us, understand how well is our model fitting. So what you see on this side is the blue line is the actual data, which was fed into the machine learning model or the statistical AR model. And the red one is nothing but the prediction. So let's say this is, you do see that there is an inherent lag and it's not fitting in very well. It is just taken the lag of it, while it does seems that it is capturing some of the peaks, but the peaks doesn't coincide with the actual value which you see here entirely. So here, if we just have to, come up, so if we just use this and try to forecast for the test. So let's say this is the actual test units sold. The model is not able to perform well here. It is just giving a flat line. So this might not be the best model for this particular use case, but still let's look into how does the, with respect to MAPE and the weighted MAPE, how is it performing? So what we're essentially saying is the MAPE value is somewhere about 20% and the weighted MAPE is somewhere about 23%. So it's not a very well generalized model, because we see that during the time of test, it seems to be failing and not able to capture the inherent peak which is happening during the holiday period. If we move on to, let's say, if you want to just try out MA model, so that's also very simple to implement. What you essentially need to do is the P and the D terms can be zeroed. And let's say we want to play around with MA value, it can be just, let's say, just try out at an order 1, meaning just the first lag value of the error terms. If we build a MA model, we do the similar of what we did previously. We take we fit the entire the model on the training data set, and then we try to predict it for the entire test. Right now, in this particular example, we have taken more than 3 data points in test and not exactly 3, but ideally you can start off using 3 or maybe try it out with different train test sample to make it work. So if you predict here and see how is it performing, it's even worse than what we saw for AR model, right? It is not able to generalize and it is not able to identify the peaks. Even it's way lower than the actual value, both during the time of training and both in terms of testing as well. If you saw here, it was still able to at least capture some trend. We do see that there was a lagged impact overall, but MA model alone is not able to capture any of the major peaks that we see or any of the trends that we see in the model. And that can rightly be seen by the error that we get. So let's say the weighted MAPE is 95%, which is way huge, meaning it's just a 5% accurate model, which might not fly in our use case. Other is if we want to use only ARMA, meaning we don't want to differentiate it, but we just want to use order 1 of AR and MA together. Does that help it get better? Similar syntax as we have seen above. if you try and fit, you'll be able to see that it is able to capture few trends, but all the holiday periods and everything, it's all missing out. So might not be the best there as well. We do see that the MAPE value is better than the MA model that we saw, but it's not like visually inspecting. We are able to see that neither it is performing well during the time of test, nor is it performing well during the time of train. Now, if we go one step ahead and move to the ARIMA model, where one of the additional terms which comes in is differentiation, as to if we just differentiate it by n number of times, does that really help it perform better? So right now, what I've taken is we have taken AR1, differentiation as 1, and let's say no MA model here. If we run this, what you'll see is also of the similar syntax as you have already seen above. We see that this is also not able to perform very well, and maybe in line with what we have seen for ARMA. We are missing out on peaks. This particular peak is coming maybe one step after the actual peak, so might not be the best model. And when it comes to forecast, that also seems pretty stagnant and not showing any better forecast for the test there. Typically, you see that what I've done is I've just hard-coded these values, 1, 1, and 0. There is like there can be an entire session talking about how do we select PTQ values. But in cases where we want to do quick iterations and there are multiple different products for which we want to really do it, those visual implementation like PACF plot or ACF plot might not be the best thing to do. There, what we have in Python is auto ARIMA, which essentially what it does is it takes in what should be the maximum value of P, what should be the maximum value of Q, and what should be the maximum value of D, and does something like hyperparameter tuning or a grid search, which essentially will do is it will take all the possible value for P starting from 0 till 3. For Q also, it will take all the values starting from 0 till 3. And for D, it will take all the values starting from 0 to 2, and then try to come up with the best algorithm or the best parameter that you should be setting up for an ARIMA model. So what it essentially does is, like I told, it will run all the possible combinations. So for AR is equal to 0, it will fine tune all the values of P, D, and Q and come up with the different forecast. And internally, you can either it runs all of those combination or it tries to understand basis the AIC, which is nothing but just one of the information criteria to understand, which could be the best possible AR value. So let's say it internally runs all of these combinations and then recommends that, okay, the best model as per the AIC information is a third order of AR term, differentiation of 1, and there is no MA associated, so no moving average there, but we just want to consider only AR by 3 and just differentiated by 1. So if we just use this particular best model after doing, so it will just split out only this particular best model. And now if we predict our test data, it will try and come up with the forecast for these. So you see, it's slightly better than, when we manually put in the PDQ values in the above ARIMA model. It is trying to get the best, which ARIMA maybe can give you with the restricted set of parameters that we mentioned here. But even now we see that we are not able to perform as well, and it is missing a lot of, especially the holiday peaks is something which it is missing out. And a little bit of seasonality is also which it's not able to capture properly. So this was the auto ARIMA, and typically that's what we use to get the best value for PDQ when it comes to getting the values out. There are different criteria even in auto ARIMA as to what do you want to maximize, which particular is it, do you want to maximize MAPE, or do you want to minimize the MAPE error term, or do you want to, you can play around with the different loss functions to make sure that you are getting the best results out. Once you have the ARIMA model, you can try the other variant is the SARIMA, where you see that there are a lot of seasonality things which it is missing out. So can SARIMA actually help us do it? In order to make SARIMA work, So the order that you see here is essentially nothing but the PDQ value. For Sarima, I think Asha must have told in the PPT that we have other terms for Sarima, which is called, so these are small PDQ. We do have capital PDQ, which is over a period of time, what's the overall differencing, or the AR term that you should be considering, what's the overall differencing at a season level that you should be doing, an MA term that you should be using, and what's the seasonality. If it's a monthly level seasonality, we typically put 12 here to indicate that it's a monthly level seasonality that we have in the data. So this will essentially saying that use a ARIMA model with value of P as 1, D as 1, and Q as 1, and the seasonal order differentiation, which is nothing but capital P, capital D, and capital Q as 1, 1, 1. And our the seasonality is monthly. That's why we have put 12. So if we run a Sarimax model, it's pretty much of the similar syntax that you saw above. You see that we are able to capture the trend, like at least for the latest season. This is a miss by the model, but when it comes to the test, it is able to perform better. There are areas where, for example, it is missing out. There are areas where this seems to be lagged as compared to the actual value, and this seems to be a major pitfall when it comes to using Sarima for our specific use case, but definitely better than all the above models that we have seen so far. And if you just look into the MAPE or the weighted MAPE, we do see that it has gone considerably down. I think the minimum that we have seen so far was 14 point something %. Now it's somewhere about 9.5%. So using a Sarimax was able to capture the seasonality over time, which was there in the sales data. Similarly, if you want to use Sarimax, you can use here I've just manually given the PDQ values and the capital PDQ values. In order to automate that has automatically been done in one of the Python the same libraries, which is the auto arima, which we imported above, where you can just give, okay, this is the training data set, and the parameter which will drive for it to start looking at the seasonality. Capital PDQ is when we do season is equal to true, it will essentially say that it's not only a ARIMA model anymore, it's a Sarimax model. So can you also play around with the capital PDQ values to come up with the best values there? So right now I've not mentioned minimum maximum PDQ here. It's just the default value that it takes, and it will come up with that, okay, if you just simply use so there is no ARMA terms associated, and maybe if you just use the first order differentiation of the season and the first order ARIMA term at a season level, it will be able to, we will be getting a better model. And if we use this parameter in Sarimax, what we see here is we do see that it is able to predict better here, but still not able to better and predict better here. And this particular part, it just seems to be a problem if we just use this order of differentiation. So meaning this might not be working the best, and we might need some PDQ values that needs to be associated with this. So this was auto Sarima, where we just try to see that if the model is performing better or not, only when it comes to Sarima, Sarima there, sorry. So it runs pretty quickly, and you'll be able to see that, okay, this is the weighted MAPE, and this is what we're showing. The weighted MAPE that you see here is with respect to the test. You can see the similar for train as well. For example, in this use case, you'll see that maybe the test is better, but the train seems to be performing a little wonky when it comes to the initial years of the time series. So this might not be the best model to use, despite of the fact that it is performing better for the test. The idea is that it probably seems to be not generalizing pretty well when it comes to train itself. Other things like we were discussing was Arimax or Sarimax, which is essentially giving it a an external variable to also look into, which will just help it understand that, okay, usually during the time of holidays, we will definitely see a peak which will be higher than the normal trends, which is going on month over month. So if you see here, what we've essentially done is just created an exogenous variable, which just says that we take the entire time series and just consider the month is equal to 12. And whenever it's equal to 12, we are giving a value of 1, else it is just giving a value of 0. So this is just, you can consider this as a flag variable, which will give 0, 0, 0 for all the months apart from 12. And for the month is equal to 12, it will just give a value of 1. So this will become as one of the features to the model, which will just say that, okay, during the month of December, you can expect a sudden peak, which will definitely happen because of the holiday period. So it's just a external variable that we have added, which is an exogenous variable, we call it. Now, if we, it's similar function, Remax. The only addition is now we are also giving the exogenous variable, which is nothing what we created here, with month value flagged as 1 for the month 12. Now, if we fit our Remax model with some of the ordered value, and this tuned it in the background to make sure that we have some better results, you see that it is able to, as per whatever we have seen previously, this was always getting missed. But now, because we have added that external variable, the model is able to capture that, okay, during the time of December, there will be an inherent peak. It was able to capture a little, but not as good as it is able to capture it once we added that particular flag variable. And that can be reflective here in the weighted MAPE, which is so far the minimum that we have achieved, somewhere about 7% of weighted MAPE for this particular Remax algorithm. Similarly, if we apply it for Max, we will have it exactly the same different parameters that we have been using. It's just that we added the seasonal order, which is what is the value for capital PDQ, and also added an exogenous variable on top of it, trained the model on the entire training data set, and predicted it for the test data. And if you see here, it's pretty similar to what we saw for Remax, maybe a little improved. That can be indicated by maybe the MAPE, the weighted MAPE value. So previously it was about 6.7. Now it's somewhere about 6.5. Still better, a little better than what we have seen so far. So Max might be, if at all we want to, just take any of the ARIMA family models, maybe for our use case, ARIMA is the right model that we can go through. Apart from that, we're just touching base on profit, because profit itself is like a very, it's a topic which can take an entire session. But if I just want to use the profit library as the library to fit this particular model in, what we do is it's just the default profit without any tuning of the parameters. If I just use profit and tell that this is the holiday flag which we are creating, that whenever the month is equal to 12, we just need to create a flag which is a Boolean value. So whenever it's 12, it will essentially give a value 1 and the remaining as 0. And we're just saying that, okay, we want to run a profit algorithm, initialize the model, and we're telling that there will be an additional external variable, which is the holiday column, which is available in the training data set. And here we're just simply fitting a model that we want. If you want to add more variables here, you can simply put it in the form of a list, and it will understand that, okay, these are the additional independent variables that we want to add on top of what profit inherently will be doing in order to aid it to perform better. So here we have fitted our training data set and then tried to predict for both the training and for the test. And if you see here, this is actually better than whatever we have seen so far. It is able to mostly capture all of it with a like maybe these are the only 2 areas which is just missing, but not with a high margin there. But if you see, the test is very accurately being predicted, and even the latest training data is also very much, it is able to understand it pretty well. And if you just look into the weighted MAPE, it has subsequently reduced. I think the best was 6.5. Now it has come down to somewhere about 4%, which is very good, and might not happen to a real use case. This is something which we just created for illustration purposes. But we see that for this particular use case, maybe a default profit model could work better if we just add a holiday feature there. There is a lot of fine tuning which might be required. So we might have to do grid search or hyperparameter tuning for profit as well. It has a lot of variables that you can play around with in order to get the best model out. But in this particular use case, what I also have is the final comparison. So we started off with normal AR model, and the weighted MAPE was somewhere about 24%. We reached to auto ARIMA, where we had somewhere about 15% error, and gradually as we keep on adding different algorithms, and because maybe the exogenous variables got added up, maybe the seasonality components got added up, or maybe an advanced algorithm like profit got added up, you could see that there's a gradual improvement in your accuracy that you see. Again, this is just for illustration purposes. It's not necessary that this is what the recommendation is, that you always start off with profit. No, it's not the recommendation. It depends from use case to use case. If you have something which is of similar trend, maybe the profit is the best model, but you have to go through and see all the different models. Maybe start off with ARIMA. These three are pretty basic and might not work for most of the things, but ARIMA to profit is something which you can try if you are for a beginner's level there, which can just help you understand and try to forecast for upcoming periods there. Yep, I think that was it with respect to the illustration for the different algorithms. I think we have time to take up some of the questions. Aditya, over to you. How do we want to take it forward?
So the first question is by Kalyani. Kalyani has put a lot of questions throughout the session. She is the founder of Ambaram.ai, which is a fashion tech platform. Her question is, can we get the presentation as email? Not possible, but we are going to release this entire session on our YouTube platform. So I would suggest you to follow us on our YouTube and LinkedIn so that you get the notification when we release it. Probably in a week or 10 days time from now, you will get this as a notification. Her question is, can we do fashion trend forecasting, use the same models? Asha, you want to take up the question?
Sure. Yeah, I think absolutely. I think traditional time series models like, ARIMA, Sarimax, or even ML-based approaches can be adapted for fashion trend forecasting. But again, fashion trend forecasting in itself has a couple of unique challenges, right? There are short product life cycles or, rapidly changing trends, and there are very strong seasonal effects. So all of these factors need to be considered. And like Jenny was mentioning, since seasonality is a major factor, Sarimax or profit can be used here. And we can also consider, in case there are additional exogenous variables that needs to be used, especially like, something related to social media sentiment or weather data. I think that can be incorporated as additional exogenous variables, either in Sarimax profit or even, ML models like random forest or XGBoost. And I think another key factor to consider is that whenever there are new products being launched, especially because it's the fashion industry, there are rapidly new products being launched. In such cases, data points will be very limited. So we might want to probably group similar products which have similar demand patterns, similar characteristics, and try coming up with an initial forecast for the new items, and then later enhance it as more and more data becomes available. So yeah, that's how, that's my take on, extending this concept in the fashion industry.
Thank you, Asha. Again, there's another question from Kalyani. Can you answer like it should be 5,000 data points? So what's the most responsible data point? I'm not sure what exactly she means, but I think she put this question when Jenny started, showing the programs and the numbers. So
Yeah.
Jenny, would you want to answer this question?
Yeah, I think I already answered this question, Amrita. I think
Okay.
there's no specific number to the number of data points that you would require. I think if the product is stable, fewer data points are required. If the product is volatile, you would need a lot more data. And I think because we want to capture seasonality, at least 2 years of data is a must. Again, Jenny, feel free to add in.
So I agree, Asha. It totally depends upon if you have like good, like you can always start off with the, trying out some of the algorithms, and if it's working fine, then you can probably use that and proceed with the forecast.
Okay. Thank you, Jenny and Asha. The next question is by Chetan Govind Swami. He is asking, do we model for every multi combinations, for example, with thousands of products sold to lakhs of retailers for a given forecasting requirement of individual demand plan for every product to retailer?
Yeah, I think depends on how many products we have, and if they have unique demand in themselves, yes, we would build a separate model for each product. And retailer is completely specific. I mean, retailer is again, it's again got to do with the brand of the product. So if the same product is being sold in two very different retailers, where the demographics are very different and the purchasing behavior of the consumers are very different, of course, we should ideally model it at a product cross retailer level.
I think agree to that. I think one of the other things is whenever we have such huge combinations, what we typically also look at is it even it does it even make sense to start forecasting for all. Many a times what we see is there's 80-20, that 20% of your customers are actually giving you 80% of the revenue. So it's better that instead of doing it for all the retailers, maybe we just prioritize some of the top ones and start doing it for them, because that's where the real value will come in and quickly. Similarly is the portfolio, that if you have such huge portfolio or the products available in the portfolio, it's better to do it for some of the top ones, because many a times what we see is there are long tails which might not be contributing to a lot of revenue. But if you just look in maybe the top 20%, 30%, it can be just seen by a simple Pareto to identify which are the retailers, which are the top contributors, as well as which are the products which across the retailers which are top contributors, and maybe start forecasting for those, get the value out of it. And if it really makes sense to get it out for all the retailers or all the products, we can probably might need a lot more computing power, but it just depends upon, we'll have to see complexity versus the revenue which will ultimately generate, even if we start forecasting for those.
Thank you, Jenny and Asha. The next question is by DK, and he is asking, can we use these models for anomaly detection also for time series data?
Yeah, I think
Yeah, Asha, go ahead.
yeah, I think if I were to rephrase the question, can we use time series model for anomaly detection as well? I think we can. We can use time series models for anomaly detection. Again, the general approach here is to use the model to predict what the expected values are, and then if the actual value is very different from what the predicted value is, then you can flag it as an anomaly. But the underlying assumption is that the model that you are building is very accurate, so that you can rely on the predictions. And once you know that the model is accurate and you can rely on its predictions, then you can forecast for a future time period, and then see if the actual value is very different from what is being predicted, then that can be tagged as an anomaly. It can be repurposed to detect outliers in the data.
Yep. And if I just give a quick example, if you remember the Excel time
Jenny,
series.
you want to add anything to that?
Yep. Can you hear me?
Yes,
Yeah.
you're on.
So I can just add one, I think one of the live
Yes,
examples was with respect to the Excel data that I was sharing. For the first example, we had like 29 and the model was predicting way higher. And the 29 did look like an anomaly. So if we just look into the error rate, that was pretty huge. That in itself indicates that because the error itself is coming up to be very high, either your model is not good, but we see that there is consistently lower error for other terms. It might be the case that the first term itself is an anomaly. So that can be a good example where once you have the predicted value from the model and the error is pretty high as compared to what we on an average see for other rows, that can be a thing which we can flag that this seems to be an anomaly. Either it's a data capture issue or some other issue which needs to be figured out.
the next question is from Pawan Kumar, and the question is, if the MAP is in 100i, is in 100, I can simply do accuracy 100 MAPE and got the accuracy. But sometimes the MAPE is crossing 100%. So how can I calculate the accuracy and why is it occurring?
I think MAPE is very scale dependent, right? So if the actual value is 10 and your predicted value is 20, that means that you're 100% off from the actual uh, demand. So there the MAPE is 100%. MAPE can be 500% as well. It just depends on what the actual value is and how different is your prediction in comparison to that actual value. So that's your MAPE. Yeah. And MAPE
Yeah.
can very well be greater
Okay.
than 100.
Jenny, you want to add anything?
Nope, I think in that case, I think he's asking if at all we're saying 1 minus MAPE is accuracy. So how can the accuracy? So typically we don't report such bad accuracies because we know that the MAPE itself is pretty high. Reporting the accuracy might not be the best thing. We might have to try out other models to see that if we can have a decent accuracy, which is less than, which is at least in the par what we require. So we essentially don't report an accuracy there because the MAPE itself is pretty huge. Then we can just say that the MAPE is pretty high for us to calculate the accuracy and might not be the best thing to calculate right now.
Yeah, and ideally, if the MAPE is greater than 100%, there is something wrong in the model. You need to fine tune the model to ensure that it predicts better.
Okay, Pawan, I think you got your answer. The next question is by Hemant, and he is asking, what if every row indicates the 4 seconds of readings coming from the IoT sensor attached to the machine? If I have 1 month of data, is it possible to train ML model for the anomaly detection?
Yeah.
Okay, I mean, it's a sincere request, like, when you're framing the question, please put it properly. Otherwise, it becomes very difficult to read. But yes, Asha, Jenny, please go ahead and answer if you understood it.
Yep. I think the question is more around, having IoT sensor readings at a 4-second granularity. And can it be used to train an ML model for anomaly detection? I think the key question here is whether 1 month worth of data is enough to capture all the normal operating conditions and potential anomalies that actually happen in that machine. So if the machine basically only behaves in a limited range for the 1 month that you've suggested, then probably the data is less for us to detect anomalies. We need to have sufficient examples in the data for training the model on anomalies and subsequently detecting it. And in an IG setup, what we have seen specifically is that each day is a different operating condition, and 1 month of data is very rich. But what we have also seen is that if the machine is dependent on say humidity, temperature in and around, then it's worth collecting that data for a longer time period so that you can detect anomalies better. I mean, that's my take on it. Jenny, anything to add?
Yep, I agree. I think if the anomaly definition itself is something which which is not getting captured in at least that 1 month of data. Let's say if you're saying anomaly as there was a system shutdown which has happened. If in that particular month you have seen let's say 30-40 times that the similar thing has happened, then probably you can go ahead and try to see if at all you can find out a pattern. But in that particular month, if none of those anomaly things has really happened for you to get it, then probably we need more data points to at least have some of those evident anomalies to be present in the training data set for it to better understand that, yeah, actually there are things which has happened. So there are times, let's say if we have 4-second data and there are things, let's say if the operators are monitoring and there are some manual inputs, maybe they would have gone for lunch and during that time something has happened. If things like these are happening, then if that's something which is available in the data and the pattern is available, then 4 months can be good because you have a lot of data points, like every 4 seconds what exactly is happening. But if the definition of anomaly itself is not something which is clearly defined in that 1 month of data, then might not be the best thing to do there.
The next question is from Kalyani again. Can we get the forecasting underscore notebook for us to practice later? Asha, Jenny, any thoughts here?
Yeah, I think we'll just need to check that once internally, Amrita, and we can try to send the notebook, but cannot promise anything. Yeah.
Okay. The next question is by Gaurav Sharma, and he is asking, what are these parameters like trace and stepwise?
Yeah. Let me just quickly share my screen. So I'm assuming you're talking about in context of auto arima, where these are the two parameters which I mentioned. So trace essentially means is we want these logs to appear so that we can see at any point of time which algorithm or which particular parameter is running. So if I just maybe make it false, you will not see these things happening and it will just automatically run. You will not see which is running and which is not running. Whereas if I just keep it as true, you will be able to see at what instance is your model. So many a times if you have a huge data set, you might want to keep a track of where the model has run. So the trace takes care of that. And stepwise, what it essentially does, when I make it false, it will go through all the iterations starting from p is equal to 0 to p is equal to 3. Like you see here, it will try all the possible combination for p, d, q if I make it false. But whereas if I make it true, it will just look into some of the so there is like an entire algorithm which runs as to which is the best combination that it will try. Either randomly it will try on some of these combinations basis how the AIC is getting impacted from one parameter to the other. So if I make this as false, this will essentially just run limited iteration and then try to give up the best on the limited scores. So in case you have, for example, one of the other questions was if we have a lot of different products, we might not want to try all the different possible combination and maybe want to restrict it to some of the top ones. Then these two parameters, like the stepwise, can help you do that, where you just want to try some of the top ones and then get the best out of the minimum lot. So this will give you the global best, and this might give you a local best that is available with the limited number of iteration that it tried.
Okay, the next question is again by Gaurav, and he is asking, what is your thought on LLM-based model to forecast? Because in real use case scenario, we have very noisy demand data, and are we planning LLM-based model forecast session?
Yep. I think specifically on LLM based model to forecast, I think it's an emerging space. And right now people are comparing the accuracy of what the traditional time series model yields against something like a chat GPT. I mean, again, it's time GPT, sorry. Time GPT versus traditional ML models is something that is being explored at this point in time. But as a, as a foundation, feeding noisy data into any sort of model will yield only noisy output. So it's important for us to have the right exogenous variables being fed into the model. And we could also try like a hybrid approach wherein there could be prediction from Surimax and other traditional methods. And we could also compare and contrast it against what a time GPT would give. And in a different context, I think there are a lot of features, text features that you could use LLMs to create structured data, and that structured data could in turn be fed into traditional time series models. I mean, that's just another way of looking at it. Yeah.
Thank you, Asha. The next question is by Mr. Nandkumar, and his question is, which model can be used for forecasting when the data is complex with features beyond date and amount that must be considered?
Again, if there are exogenous features, anything like Jenny explained, which has an X component in it, Max can be used. If the data is non-linear, then we could explore non-linear tree-based models like your XGBoost or random forest in order to predict.
Okay, so in the interest of time, I think we can take only one more question. And the question is by Pavan Kumar. And he is asking, in univariate time series forecasting, if I create external parameters using lag features, it can lead to a snowball effect of errors causing large deviations in long-term predictions. However, in this case, I do not have actual external parameters available. What are some of the effective strategies to mitigate this issue and improve forecasting accuracy?
Yeah, I think on this specific question, first of all, if it is univariate time series forecasting, we won't be able to include lag features in it. It needs to be a multivariate setup. And in multivariate setup, we can try out various lags and see which lag is significant and only include the lag which is significant. And of course, if you're going for traditional methods, including multiple lags might actually lead to inaccurate results because it could be multicollinear with each other. So trying out a tree-based approach with multiple lag variables could be one way forward.
Yep.
Okay,
And
thank
I
you.
think just to add
Jenny, yeah,
on
you can
top
add.
of it, yeah, I think when it comes to ARIMA, we have terms like AR 1, 2, 3, 4, and then the MA terms actually takes care of the error which has happened in the forecast when we started using the AR terms. So that inherently also takes care of how many error terms should we be considering, and if at all there are some rapid errors which are snowballing, which is being very evident, the MA term will be able to take care of some of the errors of the past terms and try to fine tune the model better. So in that case as well, it will not lead to a lot of snowballing because the MA term will take care of the error terms.
Insightful session of Nasscom AI Pathshala. A heartfelt thank you to our esteemed speakers, Asha Venugopal and Jenny Setia, for sharing their deep expertise in advanced demand forecasting techniques in retail. Their insights on leveraging AI and machine learning for predictive analysis from Max to Prophet provided a valuable perspective on optimizing retail operations through data-driven strategies. A big thank you to our audience for joining us today. We hope this session has equipped you with practical knowledge and sparked new ideas on how AI can transform demand forecasting and decision-making in retail. Stay connected with us on our social media platform. I have already shared the LinkedIn, YouTube, and the Twitter handle. We also have a Discord community specifically dedicated for the AI developers. So please join our Discord community, which is ever growing and evolving with a lot of knowledge, which is being shared on a daily basis by our team members. Not the least, I would like to thank my colleague Aditya for planning the session for all of us. Until next time, keep exploring, keep innovating, and see you all in the next AI Pathshala. Have a great evening, everyone.